Hello BC Calculus students, this is Mr. Johnson and we are working in section 8.3 and we're going to look at the next three convergence tests, the integral test, the p-series test, and then the comparison test. And so I'm going to throw a lot at you sort of all at once here. I'm going to give you some examples along the way. We will do one more test before the end of this section, the limit comparison test. But basically what we have at this point is test number 1, which is the nth term test, or the limit test. Test number 2, which is the geometric test. Test number 3, which is the collapsing sum or the telescoping sum. And now we have the fourth convergence test, which is the integral test. And this particular test was the reason that we did section 5.10, and we looked at improper integrals, because in this particular test what we have is a function f that is continuous, positive, and decreasing on the interval from 1 to infinity. And what we do is we map the series generator with the function so that we can look at a comparison. And the statement here for the integral test is that the series of a sub n is convergent if and only if the improper integral is convergent. Now in section 5.10, we took a look at improper integrals like this, and so if this improper integral is convergent, then the series is convergent, and not only that, but if the improper integral is divergent, then the series is divergent. So this is a very helpful test. However, you don't want to over apply it. Basically, when you look at a particular series, if you're able to take the antiderivative and you have no other options to test for convergence or divergence, then this test is probably a good test for you. So for example, we have the series, the natural log of n over n, and we're going to use the integral test to determine whether or not the particular series is convergent or divergent. One of the things I want to do quickly though is I want to show you how to walk through the tests that we've done so far. So if you look at, for instance, test number 1, which is the limit test or the nth term test, we would do the limit as n goes to infinity of the natural log of n over n. Now you could use L'Hopital's rule to prove this, but this limit is going to 0 because n will grow faster in magnitude than the natural log of n. So that test doesn't tell us anything. That's a big question mark, because if the limit is 0, it doesn't really tell us if it's convergent or divergent. If we take a look at test number 2, so test number 2 is the geometric series test. So the question is that geometric? Well, remember, geometric is going to be a value, a base, a numeric base to the power of n, which this does not have. So we don't have a geometric situation. And then test number 3 is our collapsing sum. And remember, with that one, we have a situation where we're looking for a denominator that's factorable, and the numerator is most likely going to be either a constant number or possibly a polynomial. In this case, it's a natural logarithm, and so that obviously doesn't work as well. So when you're looking through the tests that you have, you don't need to necessarily do this each time because it might be really obvious which test to use. But in this situation, we're dealing with a scenario where all of the tests that we have so far fail. They don't tell us anything, and so we need to go to another test, and thankfully we have the integral test. So we're going to take the integral from 1 to infinity of the natural log of x over x dx, and we're going to convert that into the limit as t goes to infinity of the integral from 1 to t of the natural log of x over x dx. Remember, we did all of this in section 5.10, so if some of this is confusing, it might be because you need to go back and check on that again. Now what I'm going to do off to the side here is I'm going to perform a USubstitution in order to get our antiderivative. So I'm going to look at just the integral of the natural log of x over x dx, and I'm going to let u equal the natural log of x. du is 1 over x dx. So our integral is actually, in terms of u, going to be u du, which is equal to 1/2 u squared. So that's sort of my side scratch work there. So this is going to be the limit as t goes to infinity. The antiderivative is 1/2 u, but remember u is the natural log of x, squared, and we're going to evaluate from 1 to t. So this gives us the limit as t goes to infinity of 1/2 of the natural log of t squared minus 1/2 the natural log of 1 squared. So the natural log of 1 is 0, and the natural log of t as t goes to infinity is going to be infinite. So this particular improper integral does not exist, and since it does not exist, since it's divergent, the series is going to be divergent. So what we can claim here is that the series as n goes from 1 to infinity of the natural log of n over n is divergent by the integral test. And maybe we should also add in here, because it's infinity, therefore this particular improper integral is divergent. That would help our case. Okay, so that's our first example. So that's our fourth convergence test, the integral test. All right, we're going to jump right into the next convergence test, which is the pSeries test. This is very widely used. So I would say up to this point, you have 5 tests, and we're gonna often use the first test, the nth term test. We're gonna use the geometric test a lot, and we're gonna use the pSeries test a lot. Very common one. This was actually shown, I'll just make a note here, this was shown in section 510. So what we did in 510 in those notes was that we looked at different values of p which would cause an integral. So an integral that looks like this, we looked at that in 510 to be convergent or divergent. And we came up with values of p greater than 1, which would show convergence, and p less than or equal to 1 would show divergence. And again, we looked at an integral in the form of this. So you can look back on those notes. But anyway, we basically set up the 5th convergence test, which piggybacks off the 4th convergence test. So the pSeries test is one that takes on this exact form, 1 over n to the power of p. Be really careful here, because if this number up here, let's say is 3, that's not a big deal. We can factor that to the front and just make it 1 over n to the p. But if that value is, let's say, n, so you had n over n to the p, and there's a plus 1 or something like that, if it takes on a slightly different form, we can't apply this test per se. We would have to maybe use a different convergence test. So in this example, what I'm going to do is I'm going to show you, first off, in example 2, a really simple one. So obviously this is going to be the exact form of what we're talking about with the pSeries test. The p value here is 1/2, which is, of course, less than 1. Therefore, this particular series from 1 to infinity of 1 over n to the 1/2 power is divergent by the pSeries test. And that's pretty straightforward, so it's pretty simple. Now, what if we were to tweak this a little bit? What if we were to simply just say 2 plus n squared? Can we determine if that series is convergent by the pSeries test? And the answer is no. The 2 is enough to mess things up. And so it may follow the same principles as the pSeries, but we can't use the pSeries test because it doesn't fit the exact formation of the pSeries test. We need an additional test. So again, I'm going to throw one at you right away. This is the 6th convergence test. So all of a sudden, we've just doubled the number of convergence tests that we have. We've gone from 3 to 6 in not very much time. This is the comparison test. And I find this one is used fairly often. I don't know if it's quite as common as the pSeries or the geometric series test, but it's close to it. I think they're using it more often now. What it says is that you have 2 different series, and they both have positive terms. Notice that every test we've had, for the most part, the geometric series is a little bit of a different one, but most of these tests so far have been all positive terms. Anyway, so we have 2 series, and they have positive terms. If B is convergent, and A sub n is less than B sub n, then A sub n also must be convergent. I'm going to draw you a very simple picture to convince you. So for part A here, if you had, let's say, this random series B sub n, so this is going to be B sub n, and let's say that it converges like this. And it's all positive, keep in mind. If A sub n is less than B sub n for all values, then we can visually see that B sub n sort of squeezes A sub n to converge. And that makes some intuitive sense, I hope. Now with part B, it says that if B sub n is divergent and A sub n is greater than B sub n, then A is also divergent. Well, okay, let's visualize that for a moment. So we have a similar type situation where we're comparing these two terms. So here's B sub n, and let's say that B sub n looks like this, and it continues to grow. For example, if we have A sub n and it is larger than B sub n for all values, then B sub n would basically force it, it would push it to diverge. There's no way that A sub n could be larger than B sub n and all of a sudden A sub n could suddenly converge. That would be impossible. And we can hopefully see that intuitively just by a couple examples. Now you notice this question. This is very, very common. I'm going to highlight this. This is really common in multiple choice that they confuse you with related to these two statements. So if A sub n is greater than B sub n in the first statement, so let's say B is convergent and A sub n is greater than, we really know nothing about A sub n. We don't know if it converges or diverges. It could be either one. If A sub n is less than B sub n in the second statement, we also know nothing. And it's going to be tempting to choose one or the other based on how they word the problem. And I'll show you examples of that in multiple choice. All right, let's go on to the next page. Okay, let's take a look at a couple examples here. So in the first example, we have both series B sub n and A sub n are positive, and B sub n is less than A sub n for all n greater than 1. Now with the first one, we have the limit as A sub n goes to 0. If it says if that's the case, then B sub n converges. Now, if this is true, A sub n could either converge or diverge. Now, one simple example is that A sub n, if it was, for example, the alternating harmonic, that limit is 0, yet it converges. And the harmonic, that limit is 0, and yet it diverges. So in other words, the fact that the limit of A sub n is 0 is given to us as a statement doesn't really tell us anything about A sub n, which basically means that A sub n could diverge or converge, which makes B sub n either convergent or divergent. It's a complete unknown. So A might be true, but it isn't a guarantee that it is true. Okay, for letter B, it says that A sub n converges. Now remember, if A sub n converges and A sub n is larger than B sub n, then B sub n must converge. So maybe we make a note of that. So the series B sub n must converge by the comparison test, the one we just learned. Okay, that's a true statement. Now the question is, if you have a convergent, if you know a series converges, so if you have a convergent series, you know it converges, is the limit of that series 0? And the answer is yes. The limit of that in other words, the nth term must be 0 if it converges. However, just keep in mind, the wording is so important here. If the limit of the series is 0, it tells you nothing about the series. However, if the series converges, the limit of the series must be 0. So B is our answer here. Let's go ahead and discuss the other ones just so that we learn a little something from this. So if B diverges, A must diverge. and that's going to be by the comparison test as well. Now the question is, if you have a divergent series, is the limit of the series 0? Well, it might be because the harmonic series diverges and the limit 0, but is it a guarantee? No. So C is gone. We know the answer is B anyway, but C is gone. For part D, it says that A diverges, and this is my warning that was on the previous page I just talked to you about at the bottom of that last page. If A diverges, you know absolutely nothing about B. B could diverge or converge. We have no idea. So that one's going to be gone. And then if B converges, then A, we have no knowledge of what A is doing because A could converge as well or A could diverge. And so we don't know anything. Those last two statements, those are the two different warnings I gave you, is that they're sort of tempting to choose these two. And you want to make sure to be really cautious about them because they may sound good on the surface, but if you think about it intuitively, it doesn't make any sense at all with a particular series and the restrictions that you have. All right, let's take a look at the next example. So it says, does the series converge or diverge? So we could, think through. I think it's a healthy activity as we learn all this stuff. Test number 1 is the limit test. So the limit as n goes to infinity of 5 divided by 2n squared plus 4n plus 3. That's 0. Okay, that means we know nothing of what's going on. Test number 2, is it a geometric test? No, it's not a geometric test. It doesn't have that base to the power of n. How about test number 3, the collapsing sum? Well, this is certainly a candidate in the fact that it's sort of in the style we need. It has a number in the numerator. It has a polynomial in the denominator. The problem is that the polynomial 2n squared plus 4n plus 3, that is not factorable. Remember, with collapsing sums, you must have some sort of, factorable polynomial. And so really this is not a collapsing or a telescoping sum. Test number 4, that's the integral test. And so the question is, do you want to try to anti-derive that? I don't think so. That would be kind of painful. I don't think a USub would work or anything like that. Let's see, I'm out of colors. Let's do test number 5. Okay, test number 5 is the pSeries test. Okay, well here's the issue. pSeries is the series 1 over n to the p. This has way more in it, clearly. I'm not concerned about the 5, I'm not concerned about the 2. That I can deal with both of those, but all of this extra stuff here, that's an issue for the pSeries. That's extra stuff that we don't have as part of our definition for the pSeries, so that's a problem. All right, test number 6. You can see the writing on the wall. We're going to use test number 6, which is the comparison. Now the key is, and the challenge is, what do you compare this to? So we have 5 divided by 2n squared plus 4n plus 3. Remember what I mentioned to you is that the values here that I'm highlighting, 4n plus 3, those are in the way of the pSeries test. So let's go ahead and eliminate them. Let's compare this to 5 divided by 2n squared. Now the question is, which one is larger? And if you think through division, you think through fractions, 5 and 2 are the same, n squared is the same. On the left, we're dividing by more, which means that's a smaller number. Okay, so I'll say that again. So you're dividing by more on the left, which means it's a smaller number. So we have a situation here where we're looking at, in particular, the series 5 over 2n squared. I'm going to pull the 5 over 2 out to the front so that I simply have 1 over n squared. And this is convergent by the pSeries test. Because p is equal to 2, which is greater than 1. Now, if that's the case, think about what's happening here. So we have a series that is convergent by the p-series test. We know that all of these terms are positive, so we know that everything here is greater than 0. And we know that the series we're trying to search for here is less than the series 5 over 2n squared. And so what we could say is that therefore the series from 1 to infinity of 5 divided by 2n squared plus 4n plus 3 is convergent by the comparison test. So what we're doing is we're using two of our different convergence tests in one here. We're looking through this one. We can't quite do any of the first 5 tests. They don't quite work out, but the 6th test allows us to use a comparison of something that we know from a different test, the p-series test. We're utilizing the p-series test for one element, and then we're going to work that into the series we're trying to search for here by using the comparison test. Okay, let's go ahead and take a look at the last example. And this one is the exact same problem that we had in example 1, so the first example of this video. However, in the example 1, we used the integral test to determine convergence or divergence. And what we're going to do here is take a look at the same exact series, but we're going to use the comparison test. So one of the things to keep in mind here is that you can use sometimes multiple tests to determine convergence or divergence. And so you want to obviously pick the one that's maybe the easiest to use. And then other times, of course, there may be only one convergence test that you can apply to a problem. But in this case, we could either do the integral test or the comparison test. So we're going to look for something to compare to the natural log of n over n. And we want to find something that is similar to this expression, but something that we do know in terms of convergence or divergence. So the one that comes to mind here is 1 over n. And we know 1 over n as a series is divergent because it's the harmonic series. And we do know that ln of n over n is going to be larger than 1 over n because the natural log of n is in the numerator. We'll make that one grow faster. However, if you think about, let's say if n was, let's just say if n was 1, for example. So if n is 1, we have the natural log of 1 over 1 and 1 over 1, and the natural log of 1 is 0. So you end up getting 0 is greater than 1. That's obviously a false statement. And so in this particular case, we have to just be careful that we're not making a false claim. The statement that we're making here is true as long as n is greater than e. Now, we really are looking at a series in the context of n going to infinity. So we don't really care necessarily if our comparison here is false earlier on. We care about what happens as n grows really large. But just by definition, just so that everybody's aware, if n was equal to e, we have the natural log of e divided by e is greater than 1 over e, and that gives us natural log of e is 1. So we have 1 over e is greater than 1 over e. That's still false because we're not equal to, but the key is that if n is greater than e, then this particular comparison is going to be true. And again, care about what n is doing as n gets really large. Okay, so we have a comparison that we're looking for. Now I mentioned that the series from n is 1 to n is infinity of 1 over n is divergent. And that's true because it's the harmonic series, but we could also say by the p-series. And p is equal to 1 here, which is our restriction for divergence. And so we have a divergent series that is less than another series. So just think about it intuitively. If you have a divergent series that is less than another series, that divergent series will push the other one to also diverge. So then what we can say is that the series from n is 1 to infinity of the natural log of n over n is divergent by the comparison. And this is also sometimes called the direct comparison test. All right, so that's an example of how we can get the same result that we got in example 1 by using the integral test, but now we're using the comparison test. I think you would agree that the comparison test in this context is much faster, but the challenge is that you have to find a particular series to compare it to that ends up making some sense. And that's the challenge versus the integral test, which is more of a challenge just because you're doing a USubstitution and you're having to perform the antiderivative and so on and so forth. All right, that does it for the first 5 examples in section 8.3. So in the next video, we'll tackle another convergence test. Thank you.